In this chapter, we're going to talk about the basic model of consumer behavior. So we're going to be thinking about the model of utility maximization, and we'll talk here in just a second about what utility is. You may have talked a little bit in a previous class, maybe a Principles of Micro class, about the idea of utility. Utility is just the economist's word for well-being. But we're going to go into a lot of depth with that model, and we're going to use that model to try to understand a lot more about where demand curves come from. So let's start with what the basic consumer's problem is. And the consumer's problem, we're going to think about it in terms of the consumer maximizing their well-being given the resources that they've got to work with. And the resources that they've got to work with that's going to be their income. So the consumer is going to use their income to try to maximize their well-being. And that's not just monetary well-being. Their well-being can be determined by the well-being of people around them, other things like that. What we need to do is we need to talk about some basic assumptions of consumer preferences. So what we want to do is we want to assume some things about consumer preferences, some very simple things that are reasonable assumptions to make, and then from those assumptions, we'll develop this model that we use to understand behavior. The first one that we're going to think about, the first assumption that we're going to make about human behavior is what we call completeness and rankability. Completeness and rankability. And the idea here is that given any two bundles, A and B, the consumer can decide if they like A more than B, or B more than A, or if they're indifferent between the two. So if we have two bundles, A and B, and a bundle would just be some combination of things. Now we're going to keep our life simple, so we'll assume that we're going to start with a model where there are just two goods, maybe books and movies. And so given some combination of books and movies and another combination of books and movies, the consumer could decide whether they like this bundle better than that one, or that one better than this one, or whether they're indifferent. Sometimes we write it this way. If the consumer likes A more than B, we would write that. Or if they like B more than A, we would write that. Or if they're indifferent, we would write that. And here we're thinking about a bundle. Okay, so some combination of the goods. That would be the bundle. So that's the first assumption that we're going to make, that if I give you two bundles, you can decide which one you like. Or it's fine if you decide that you're indifferent between the two. Okay? And that's a reasonable assumption to make. So they can rank the bundles. The idea of completeness is that we can do this with any two bundles. It doesn't matter which bundles I choose, you can rank them. Okay? So that's the first one. The second one is that more is better than less. So the idea here is that we're thinking about goods. And if you think about that term, a lot of times if you've had economics classes, you've heard the phrase goods and services over and over and over, and you may not have actually stopped to think about why we call them goods. And the reason that we call them goods is that they're good. They provide us with well-being. If we're thinking about something like pollution that we would like to have less of, we call those bads. And so a good is something that makes us better off. And so we're going to be making the assumption that more is better than less. Now, you might be thinking to yourself, well, I can come up with exceptions to this, where even something that provides me with well-being, more is not better than less. And so maybe an example I could come up with would be pizza. I like pizza, but if I went home and my house was completely filled with pizza to where I couldn't even get in the doors, then clearly more is not better than less. Well, we're not thinking about crazy, weird situations like that. Actually, the way that you can rephrase this to where it makes more sense is we could say that we'll call this assumption free disposal. The idea here being that if you did get to a point where you were overwhelmed with the quantity, you could just snap your fingers and it's gone. Okay? But the idea here is that more doesn't make you worse off. So more is better than less, and for goods, that's a reasonable assumption to make. Another assumption we're going to make is this assumption of transitivity. And this is a very straightforward thing. It makes perfect sense once you think about it. So if we're considering three bundles, A, B, and C, then we can say this: if the consumer likes A more than B, if the consumer likes A more than B, and B more than C, then that means the consumer has to like A more than C. If they like A more than B and B more than C, they have to like A more than C. And that's a reasonable assumption. I've had students try to come up with exceptions to this, and I would challenge you to try to do that. You can't come up with a reasonable thing where you like this more than that and that more than this, but somehow you like that more than that. You're not going to be able to come up with one. So this idea of transitivity, that's a reasonable assumption to make. And then we're going to make one final assumption, and we're going to call this one diminishing marginal utility. Diminishing marginal utility. The idea here is that the more of something you have, the less you're willing to give up to get another unit. Okay? So if you don't have very much of something, you may be willing to give up a lot at the margin to get one. But the more of something you have, if you've already got a whole bunch of it, you're going to be willing to give up less to get another unit of it. Okay? So those are the assumptions that we're going to make about consumer preferences. And you can see that those are reasonable assumptions, and what we can do with that is we can develop an entire model of human behavior that is extremely useful in understanding why people do the things they do and predicting what people will do in the future, depending upon the incentives that they face. So what we're going to think about now is this model, the utility maximization model. So let's think about the idea of what utility is. And so utility is just going to be our measure of the well-being of consumers. So it's a measure of the well-being of the consumer. So goods provide us with utility. They provide us with well-being. What we're going to do is we're going to think about representing the well-being, the utility of a consumer, with what we call a utility function. A utility function. And this is actually going to be a mathematical function. It's going to be a function where we can plug in the number of units of each good that the consumer is consuming, and out of that will pop a number, and that number will represent the well-being of the consumer. So let me write a general representation of a utility function. We could write it like this. Utility is some function u of x and y, where these are the goods, x and y are the goods, a particular combination of x and y would be a bundle, and then u represents the amount of utility that the consumer gets. So these are the goods, this is the amount of utility, and then this u, which we could write this way, if you don't want to, you want to write it in its most simple form, we could just describe it as some function u. I'm not going to write the arguments of the function. I'm just going to put a dot in there because all I want to do is focus on this function. That's going to be a mathematical function. So if we think about some examples, Once you see examples of it, you start to realize this is very straightforward. A utility function could look like this. It could be x multiplied by y, where you take the number of units of x and the number of units of y, you multiply that together, and that gives us the amount of utility that you get. Or we could have another utility function be x plus y. Or we could have what's referred to as a Cobb-Douglas utility function, which is a very, very useful utility function. It's more complicated than these. These are nice and simple. This one looks like this. A Cobb-Douglas utility function, we could have x raised to the 1/2 power times y raised to the 1/2 power. Now, anytime you raise something to the 1/2 power, all you're doing is you're taking the square root of it. So this is the same thing as writing this. Utility is equal to the square root of x multiplied by the square root of y. That's what that utility function looks like. So for example, let's suppose we had 2 units of good x. No, let's say 4 units of good x and 4 units of good y. Well, using this utility function, we would get 16. Our u would be 16. The units of measure that we use, we call utils. So if we had 4 units of x and 4 units of y, 4 times 4 is 16, so we would get 16 utils. With this utility function, 4 plus 4 would be 8. With this utility function, the square root of 4 is 2, multiplied by the square root of 4, which is also 2, we would get 4 utils. Now let's pause for a second and talk about utils and utility function. If you go back to the early history of the utility model, it was invented by Jeremy Bentham. Jeremy Bentham was an economist, an unusual economist. What Bentham is best known for, besides his work in economics, which was groundbreaking, and we still do a lot of the things that Jeremy Bentham came up with. He's best known for making a lot of money during his lifetime and then leaving that money in his will to one of the economic schools in England. It was a university. I can't ever remember what the university was. I always want to say that it was the London School of Economics, but it wasn't. But just for the sake of the story, I'm going to just use that school. So he left his money in his will to the school, but in order to get the money, what they had to do was they had to essentially mummify his head. They had to take his body, remove the flesh, the organs, articulate the skeleton, put his clothes on the skeleton, mummify his head with the skin preserved on it, and then build this thing. It's basically a display case called the auto-icon. And they had to put him in the auto-icon with his feet between his legs. And they did, and you can still see Jeremy Bentham's mummified head to this day. If you'll Google auto-icon, you will find pictures of his body, his clothes sitting on a stool, and his head between his feet. They did make, it's a long, interesting story. The head got stolen by a fraternity. They replaced it with a wax head that actually looked like Jeremy Bentham. The real head kind of went bad in the preservation process, and it's weird looking. And then they recovered the original head, and so now they've got both the heads there. It is an unusual thing. But Bentham came up with this idea of utility. When he came up with it, he thought that we would actually be able to come up with a device that measured utility. Bentham was around when the thermometer was invented, and so he observed that we had now this device that we could measure the internal temperature of a human body, or we could measure the temperature of physical objects. Hadn't been able to do that before. And so he thought that through advances in science, eventually we would come up with what he was going to call a utilometer. And a utilometer was going to be a device that could be used to measure human happiness. And with a thermometer, you measure it in degrees. his utilometer was going to use utils. Okay? Now he realized in his life that the utilometer was not going to be invented and that it just wasn't something that you could measure. But we still use this model of utility maximization. It's still very, very useful. Okay, so Jeremy Bentham came up with this. Let's talk about marginal utility. Okay, so the idea of marginal utility should be very straightforward to you because you've talked about marginal things in principles of macro, principles of micro. You've talked about marginal cost and marginal benefits. You've talked about lots of different marginal things, marginal product. So marginal utility is just the change in utility when you consume another unit of the good. Now our utility functions have two goods in them, x and y. So we can think about the marginal utility of x and we can think about the marginal utility of y. We will write them this way. The marginal utility of good x is going to be the additional utility that you get from consuming one more unit of good x. I'm going to write it this way. The change in utility when you change good x. It's nothing more, if you've had calculus, it's nothing more than the derivative of the utility function with respect to good x. Now, anytime you've got a function that has two arguments, two variables, then you have to take a partial derivative. But the marginal utility of good x is just the partial derivative of the utility function with respect to good x. Okay? We're not in this class going to be doing the calculus of it, but that's what it is. It's just a derivative. We can also think about the marginal utility of good y, and it's going to be the change in utility when we change good y. It too is a partial derivative, only it's the partial, let's write it this way, marginal utility of y is the partial derivative of the utility function with respect to good y. So we've got our marginal utilities. Let's talk about now how to use this concept of utility to make comparisons between bundles and how we're actually going to use this. So let me clear this off and then we'll talk about making comparisons. So let's talk about the way that we can use the util number. Once you plug in a bundle into the utility function and you see how many utils you get out of it, let's think about what that number means. So what we're going to do is we're going to be able to use that number as an ordinal ranking. It provides us with an ordinal ranking, but it does not provide us with a cardinal ranking. Now let's talk about what that means. Let's suppose we have three bundles. So consider three bundles, A, B, and C. And let's suppose that when we plug remember each of these bundles contains a different amount of good x and good y. Okay, so these bundles are all different from each other. Let's suppose that when we plug the bundle into the utility function, we get 6 utils from A. A gives us 6 utils. We get 4 utils from B. And let's suppose we get 12 utils from C. Now we would be plugging this into the same utility function. I had an example down here where I had 3 different utility functions and we took one bundle and plugged it into 3 different utility functions. We're not doing that. We're taking 3 bundles and plugging them into the same utility function. So we get these numbers that come out of that. What we can do is we can say that the consumer prefers A to B and the consumer prefers C to both A and B. Okay, so the ranking that we would get is that they prefer C and then A would be next and then B would be last. So that would be the way that the consumer would rank these bundles. If they could choose, they would choose C first and then they would take A and then they would take B. What we can't do is we cannot look at these numbers and say anything about how much the consumer likes one bundle compared to another. So we would never say that the consumer likes bundle C twice as much as bundle A. The difference between 6 and 12 doesn't matter. All that matters is that 12 is bigger than 6. Okay? So it provides us with the order. That's what it means to have an ordinal ranking. It gives us the order, but it doesn't give us anything about the cardinality. If this was a cardinal ranking, then we would be able to say that they like C twice as much as A. The cardinality tells you something about the difference between these two. We don't use the utility function that way. Okay? We only use it to order bundles. We would get the same outcome. If we got 14 utils from A and 2 from B and 101, let's say, from C. Well, suppose when we plugged it into this utility function, it gave us these numbers. This gives us the same information as that. It gives us the same order. The difference between these three things does not matter. Okay? Here's another thing. We can't make interpersonal comparisons. So if we were to take a bundle A, and plug it into your utility function, and then plug it into my utility function, we would never make an interpersonal comparison and say that I like it more than you or you like it more than me. That would be using the cardinality of the number, and we can't do that. Okay? So we're only going to use a single person's utility function to rank bundles for them, and we don't compare the utility number across people. The other final thing we have to talk about a utility function is that the utility function can change over time. Okay? Your utility function right now does not look like what your utility function is going to look like in 20 years. Let's talk now about what we're going to call indifference curves. So this is how we're actually going to put this model into practice and use it to come up with demand curves. So in order to motivate what we mean by an indifference curve, let's think about a simple situation where there are only two goods, and let's suppose there are movies and books. And I'm going to draw my picture over here. Let's suppose that, make this kind of big. Let's suppose we put books up here, and we'll put movies down here. And I'm going to number my axes so that we can actually think about some particular points on here. I'm going to have 5 and 10, 15, 20, 25. And let's do the same thing with our horizontal axis. Up to 25. Now let's pick a bundle to start with. Let's suppose that we start with, say, 15 books and 10 movies. And that would be this bundle right here. 15 books, 10 movies. That's that bundle. We'll call it Bundle A. Bundle A contains 15 books and 10 movies. What we want to do is we want to be able to say something about how Bundle A compares to other bundles on this picture. There's an infinite number of bundles on this picture. What we can do is I can kind of extend this dotted line up like this, and I can extend this one over here, and we can easily, using the assumptions that we made about consumer preferences, we can compare Bundle A to a whole bunch of other bundles on that picture. So for example, we can compare Bundle A to any bundle down here, and we know that the consumer would prefer Bundle A to any of these bundles because Bundle A contains more of the two goods than any bundle down here to the southwest of A. We can also say that the consumer would prefer any of these bundles up here to A, because these bundles up here would contain more of at least one of the goods. So we can now talk about A compared to all of these bundles and compared to all of these bundles. Now we can't say anything about these bundles up here or these bundles down here. These bundles up here have more books than A, but less movies. And these bundles down here have more movies, but less books. So we need to figure out something about these bundles down here and those bundles up there. So what we're going to do is let's consider kind of a thought exercise. Let's suppose that we take away 5 books from our consumer, and then we ask them to think about how many more movies we would have to give them to make them just as well off as they were at point A. Okay? So let's suppose we take 5 books away and ask them how many more movies they need to be indifferent between our original point and this new point. And let's suppose that they say that if we give them 6 movies, then they're just as happy as they were at A. So suppose we give them 6 movies. Now that takes us to this point down here. We're taking away 5 books, but we're giving them 6 movies. So that takes us to a point where we've got 16 and 10. That takes us to this bundle that we'll call bundle B. Okay, and let's make sure that we identify that that's 16. Here's bundle B. Now, by definition, the way we've done this, the consumer is indifferent between A and B. Right? They don't care whether they're at A or whether they're at B. We've taken away some books, but we've given them enough movies to leave them just as happy as they were before. But now notice what this allows us to do. This allows us to talk about a whole bunch more bundles that we couldn't have discussed before when we just had point A. We can now talk about comparing any of these bundles down here. Of course, we can compare these bundles to B, and we can compare bundles up here to the northwest of B, but we can also compare these bundles to A, because we know that the consumer is indifferent between A and B, and they like B more than any of these bundles, so they like A more than any of these bundles. We also can talk about bundles up here. A bundle like this one, the consumer would prefer to B. They are indifferent between B and A, so they would prefer this bundle to point A. So this allows us to talk about a lot more bundles on this map than we could when we just had point A. So now let's do this again. Let's take another 5 away. Another 5 books away. And let's ask the consumer how many more movies they have to get to be indifferent between B and this new bundle that we're going to call C. So we're going to take another 5 books away and give them some movies. Now let's think about how many movies we have to give them. Starting at point A, we took 5 books away and we had to give them 6 movies. Think about when we take another 5 books away, how many more movies we're going to have to give them and whether or not that's going to be more or less than 6. And if you remember back to that last assumption, you'll remember this law of diminishing marginal utility. The more of something you have, the less you're willing to give up to get another one. Well, the other side of that coin is the less of something you have, the more you're willing to give up to get another one. So as we take books away and they have fewer and fewer books, we're going to have to compensate them more than we did before because they're moving down in this direction where they have relatively few books. So when we take another 5 away, so now we're down here at 5 books, we're going to have to give them even more movies. Let's suppose we have to give them, I don't know, let's say 12 movies. So that would take us out to a point like this. It'd be, say, 28. That gets us to another point, point C. So the more of the books we take away, the more we have to compensate them. This is the same idea as why the best bite at the buffet is the first bite at the buffet is the best one. As you have few bites, you value them more. If you've already got a lot of them, you value them less. And up at A, we've got relatively a lot of books, so they don't value them quite as much as they do when we start taking them away. And out here at C, they value books at the margin highly. This gives us, so now we have to give them 12 movies, and that takes us to bundle C. Now notice that the way we have constructed this, they are indifferent between bundles A and B and C. We are finding bundles that they are indifferent between. And remember, what we're trying to do here is find an indifference curve. An indifference curve represents all of the bundles on that picture that they are indifferent between. So the indifference curve that would go through point A would also go through point B and would also go through point C. Now, if we were to take more books away, we would have to compensate them with additional amounts of movies. And you can tell that what's going to happen to this indifference curve is it's not going to be a straight line, it's going to be a curve. And it's going to come down here through A and through B, and as we move in this direction, it gets flatter and flatter. As we move in this direction, it gets steeper and steeper. Okay. So if I want to leave that, but let's just think about what I just said here. Here we've got books. Here we've got movies. And let's start here with our bundle A. What we did was we found 2 more points, but what that indifference curve is going to look like is it's going to come through A and through B and through C, and it's going to be curved like this. That's an indifference curve. We're going to call it, U1, because remember, any point on this indifference curve, whether it's A or whether it's B or whether it's C, all of those points give us the same number of utils. If we plug any of these bundles into the utility function, we will get the same number out. The consumer doesn't care whether they're at A or B or C or this bundle down here or that bundle up there. They're indifferent between all of them. If we were to think about now comparing any bundle on this indifference curve to a bundle like this one, that bundle right there, that bundle is going to provide a higher level of utility than any of the bundles on this indifference curve. That bundle would actually be on a higher indifference curve, one that might look like that. We could call it U2. It provides us with a higher level of utility, and we know that because it contains more of both goods than this bundle B down here. Okay? It's on a higher indifference curve. Let's talk for a second about the characteristics of indifference curves, and then I'll give you kind of an intuitive explanation for what we're talking about here. So let's think about some indifference curve characteristics. Let's just squeeze it right in here. Characteristics of indifference curves. The first one is that we can draw them. That's the first characteristic. And that comes from the assumption of completeness and rankability, that first assumption that we made. In other words, we can say that the consumer is indifferent between A and B and C, and we can also say that if we called that bundle D, the consumer would prefer bundle D to bundle B because D has strictly more of movies and books than B. So we can say that the consumer prefers D to B, and they would prefer D to A or D to C. Okay? So we can draw indifference curves. Curves farther from the origin represent higher levels of utility. So curves farther from the origin represent higher utility. And this comes from the assumption that we made that more is better than less. Another characteristic of indifference curves is that they never cross. Indifference curves, I'm going to abbreviate that. Indifference curves never cross. That would violate those assumptions that we made about preferences. Let me show you why. Let's draw two indifference curves right in here. Let's suppose I had an indifference curve that looked like that, U1. And then somehow I drew another indifference curve that looked like this, and I made it cross U1. So there's U2. I'm going to put point A right here. Point A is the point at which they cross. That means that the consumer is indifferent between point A and any other point on those indifference curves. But now let's compare this. Let's compare point B to point C. What I know is that since A and B are on the same indifference curve, the consumer is indifferent between A and B. But I also know this. Since A and C are on the same indifference curve, the consumer would be indifferent between A and C. So if the consumer is indifferent between C and A and indifferent between A and B, they should also be indifferent between B and C. But yet C contains strictly more of the two goods than B. That's a violation of the preferences, the assumptions that we made. More is better than less. So indifference curves can't cross, and that will be, once I show you kind of intuitively what's going on here in a second, I think it will be even more clear why indifference curves can't cross each other. And then finally, they are convex to the origin. Convex to the origin. What that means is, let me draw one final picture down here. Indifference curves will never look like this. What this means is that the less of something you have, the less you're willing to give up to get another unit. This would be consistent with the last bite at the buffet being the best one. That we know that that's not how humans behave. That's not how people's preferences work. So they aren't shaped like that. Concave and convex, the concave part of a function is like the cave part, like that. This side would be concave. This side over here would be convex. So if we're taking the point of view of the origin, this indifference curve is concave to the origin. These indifference curves, when viewed from the origin, they are convex. So indifference curves are convex to the origin. What I want to do now is clear this off, and then we'll talk intuitively about what these indifference curves and what the utility function actually looks like if we visualized it. Let's take a second and just think about what this utility function is representing. So if we thought about the utility function that we're thinking about, which is utility as a function of two goods, x and y. If you think about the picture that we're going to put right here, the utility function is like a big pile of sand sitting in a room. Okay, and so if you think three-dimensionally, along one corner or edge of the room we could put the x-axis, and then the other corner we put the y-axis, and then vertically we measure utility, then the utility function is just this three-dimensional object, and as you have more x and more y, you get higher up on this utility mountain. Now the indifference curves are represented as a height on this mountain. You can see the indifference curves here. And the idea of an indifference curve is if we were to take, say, a clear piece of plexiglass, suppose that mountain was made of sand, and we could take a clear piece of plexiglass and just stick it right through horizontally, right into that mountain of sand, then the indifference curves would just trace out the outer edge of the mountain on the piece of plexiglass. And so the indifference curves are, if we were above this picture, looking straight down on the floor, then that's what you're seeing with the indifference curves. That's why they show up as a curve. So the utility function, at least three-dimensionally, if we're thinking about the utility function as being a function of just x and y, we can easily draw a picture of it. Now, the idea behind a utility function and the idea behind the indifference curves is very similar. Actually, it's the exact same idea to a topographic map. And so if you look at a topographic map, this will help you understand why the indifference curves can never cross. So if we take a look at this topographic map, what you'll see is that essentially what it does is it traces out, each line corresponds to a particular elevation. And so if you think about the way that mountain of sand would look, it's going to be a series of circles. If the mountain was circular, it would just be a series of circles, and at higher elevations, the circles would get smaller and smaller. So if you look in the top left of the picture here, you'll see something that looks very similar to kind of this mountain of sand. And you can also understand why these indifference curves can't cross, because it doesn't make any sense. If the lines represent an elevation, it doesn't make sense for them to cross because they exist at different levels of elevation. And so indifference curves can't cross for the exact same reason that the isobars on a topographic map can't cross each other. Now, it turns out that if you know anything about geography, you know that if you have, let's say, a mountain with a cave in it, then actually on a topographic map, the isobars could cross if we had that cave. Well, we're not going to be having caves in our utility function or anything like that. So if we just have a topographic map of a big pile of sand, then none of the isobars would cross each other. Now, we also know that when we think about indifference curves, we're only going to be thinking about the portion of the indifference curves that look like this. Our indifference curves always have to be negatively sloped. They have to be negatively sloped. They have to be convex to the origin, because if they weren't, if you looked at an indifference curve that say was positively sloped like that would not make any sense, right? Because this would say that if we had a point like A and a point like B, because those are on the same indifference curve, the consumer would have to be indifferent between A and B, but yet B has more of both goods than A. So we can never have any upward sloping portion of an indifference curve. What that means is we're never going to have indifference curves that curve back up like this. So when you look at the topographic map, you're going to see things that look like this. Well, since we're talking about indifference curves, we're never going to have this portion of any of that. We're only going to be thinking about the downward sloping part, because that's the part that's consistent with human behavior. So this indifference curve picture that we're using, you need to think about it as really just a topographical map of somebody's preferences. That is exactly what it is. Now, we're always going to be using the two-dimensional picture like this, and that two-dimensional picture is representing a three-dimensional idea. Okay, so this indifference curve, ignore these portions right over here. This indifference curve U1 would be at a lower level of utility, a lower elevation than this indifference curve or this indifference curve. Okay, they're representing higher levels of utility as we get farther from the origin. So hopefully that gives you an idea of what this picture really represents when we're drawing these indifference curves. Let's talk now about what we're going to call the marginal rate of substitution. The marginal rate of substitution is simply the slope of the indifference curve. Marginal rate of substitution is going to be the slope of the indifference curve. So let's draw an indifference curve here. Let's go ahead and put good x down here and good y up here. If we were to think about the slope of an indifference curve, I'm going to draw a line that's just tangent to that indifference curve at this point right there. So if we were interested in the slope of this indifference curve at that point, it's going to be equal to the slope of the line tangent to the indifference curve at that point. So let's think about the slope of this line that's just tangent. So remember, the slope is the rise over the run, and we can think about this rise. This is the change in y, and this horizontal distance is the change in x. If we were thinking about taking good x away and giving them good, or taking good y away and giving them a particular amount of good x, then we could think about this rise over the run, and the slope of the indifference curve right there is going to be what we call the marginal rate of substitution. Marginal rate of substitution, we always write it with the good on the horizontal axis first. We say the marginal rate of substitution of good x for y. We're taking y away and giving them good x, and it's going to be equal to the slope of that indifference curve, which is the change in y over the change in x. We typically put a negative sign out in front of it because this has a negative slope, and that negative is going to cancel it out and make it a positive number. So let's think about what the marginal rate of substitution tells us. What does it mean? It simply tells us how much of one good we have to give them in order to, if we take some of the other good away, in order to leave them as well off as they were before. So let's do a quick example. Let's suppose that we have an indifference curve and we think about a point like point A first, and then let's compare it to a point like point B. Now the consumer is indifferent between point A and point B. Let's go ahead and put our movies and books back on here so I can talk about goods. Let's suppose that if we look at the line that's just tangent at point A, it's going to be something like that. Let's suppose that that has a slope of 3 over 1. It's a slope of 3. What this means is that if we take, at this point A, if we take 3 books away, we can give them 1 movie and they are just as well off as they were before. On the other hand, let's look at the slope of the indifference curve at point B. And clearly the slope is smaller in absolute value. Let's suppose that the slope down here is 1/3. What this means is that if we take 1 book away, we have to give them 3 more movies to leave them indifferent. And the reason is, compared to point B, or excuse me, starting at point B, compared to point A, we've got relatively few books down here at point B. So if we take another book away, we have to give them 3 movies. The idea here is this diminishing marginal utility, right? The more of something you have, the less you're willing to give up at the margin to get another unit. The other side of that is the less of something you have, the more you are willing to give up to get another unit at the margin. So let's think about what this looks like. Okay? And I'm going to do something here that your book goes through. This is not something that I would ask you to go through on the test, but it is something that hopefully will help you understand the next result that we get. I'm going to think about what happens if we change utility. So let's suppose we have a change in utility. Now a change in utility would come from either a change in good x or a change in good y. If we thought about our utility function as being a function u of good x and good y, then changing either x or y will change utility. Or if we changed both of them, it would change utility. Now how much utility changes depends on how much we change x and how much we change y. and it depends on the particular functional form that we're using. Okay? So we can think about the total change in utility, and if you've had a calculus class, you can think about this as, say, a total derivative. This is the same idea. Okay? So our change in utility is going to be the change in movies, let's say change in quantity of movies, I'm going to put an M down there, multiplied by the marginal utility of movies. How much movies change? Multiplied by the marginal impact of changing movies, plus change in the quantity of books, multiplied by the marginal utility of books. So we can think about that as a total differential. So the total change in utility depends on how much movies change and how much books change, plus what the marginal impact of movies and books is. Now, if we consider moving from point A to point B, utility will not change. So I can make this a 0, and then we can use this to get something useful. So if we think about moving from point A to point B, because they are indifferent between A and B, the change in utility will be 0. So 0 equals the change in quantity of movies times the marginal utility of movies, plus a change in the quantity of books times the marginal utility of books. I'm going to move one to the other side. Let's move marginal utility of book. Let's move this term to the other side. So we get negative change in the quantity of books times the marginal utility of books is equal to the change in the quantity of movies times the marginal utility of movies. And then let's move some terms around. I'm going to take this marginal utility, I'm going to divide both sides by that and move it down here. I'm going to divide both sides by delta QM, and that's going to move it down here, and I'm going to get this term. The change in the quantity of books divided by the change in the quantity of movies, and I've still got that negative sign over there, is equal to the marginal utility of movies divided by the marginal utility of books. Now again, I'm not going to ask you to work through the algebra of that. That's not important. But it's useful to see that so that you understand this statement right here. What this tells us is, this statement is essentially what I've got right there. This is the change in the good on the vertical axis, our rise, divided by the change in the good on the horizontal axis, our run. There's our rise, there's our run. And what this tells us is that the marginal rate of substitution is equal to the ratio of the marginal utilities. It's the marginal utility of the good on the horizontal axis divided by the marginal utility of the good on the vertical axis. And that is extremely important. So let's make sure that we know that the marginal rate of substitution, let's write it now in this notation. Marginal rate of substitution of good x for good y is equal to the marginal utility of good x divided by the marginal utility of good y. Okay? Marginal rate of substitution is the ratio of the marginal utilities, and you always put the marginal utility of the good on the horizontal axis on the top in the numerator. Now we're going to come back to that here in a future video, and we're going to use that. Actually, it will pop up a couple of different times throughout the class. Let's clear this off, and then we're going to think about kind of the steepness of the indifference curves and the curvature of the indifference curves. Let's think about the steepness of indifference curves for a second. So if I were to draw a set of indifference curves, and remember, the shape of the indifference curves is going to be determined by the three-dimensional shape of the utility function. So if you think about that utility function, it's going to be three-dimensional. If you think about, here's our x-axis and our y-axis, it's a three-dimensional pile of sand that just kind of rises up like this, and it has a peak out here. So I could push that pile of sand to one side, or I could push it to the other. I could make it really steep on one side and not steep on the other. And then if I were to draw the indifference curves that represent lines of equal elevation, then the shape of those indifference curves is going to be determined completely by what that big utility function looks like. So let's suppose that the indifference curves, when we draw them, are very steep, like this. And let's go ahead and put movies down here and books up here. What this would mean is that consumers are willing to trade a lot of books for a few movies. These things are very steep. And so if you think about what's going on here, this means that if we consider this point and that point, the consumer's indifferent. They're willing to give up a lot of books for just a little bit more movies. That's completely different than if we drew the indifference curves. And let's again go with movies and books here. If when we drew them, the indifference curves were very flat like this, then what this would tell us is the consumer's willing to give up relatively few books to get a lot of movies. In other words, if we think about going this way, the consumer, if we consider this point and that one, the consumer's willing to give up a lot of movies for a little more books. So the steepness of these indifference curves tells us something about how much the consumer likes this good versus the other good. We can also think about the curvature of indifference curves. And the curvature is going to tell us something about how substitutable the two goods are. So if we think about two goods that are very substitutable, and so we could think about, say, red shirts and blue shirts. Red shirts, blue shirts. Those are very substitutable, and in that case, the indifference curves are going to have very little curvature. Going to look something like that. Or we could think about goods that are very complementary to each other. A high level of complementarity. Those would be things like shirts and pants. Let's put pants up here and shirts down here. Those certainly are not substitutes for each other, and they go together. In that case, there's going to be a lot of curvature. Now notice those are still downward sloping, they're convex to the origin, but they've got a lot more curvature than these indifference curves. We still would say that indifference curve U3 corresponds to the highest level of utility. All of the usual things still pertain, but the curvature tells us about how complementary the goods are. Let's talk about perfect complements and perfect substitutes. So if we were to think about two goods, and this hopefully will help you understand why the curvature matters a lot. If we thought about two goods that are perfect complement, or let's say perfect substitutes, let's suppose that for you, Coke and Pepsi are perfect substitutes. You do not care at all which one you have. Then let's put, say, cans of Coke down here. And let's put cans of Pepsi up here. And let's think about what the indifference curves would look like. Let's put, say, 1 can, 2, 3, 4. And let's consider this point right here. Let's suppose that we thought about that point where you've got 2 cans of Pepsi. Let's think about other points on this picture that you would be indifferent between. You would also clearly be indifferent between this point and this point down here, where instead of 2 cans of Pepsi, you've got 2 cans of Coke, if they're perfect substitutes for you. And you would also be indifferent between that point. where you have one of each. And so that should be right in here. What we see is that when we draw the indifference curves, they're perfectly linear. They have no curvature in the case of perfect substitutes. If they're not quite perfect substitutes, but they're still very substitutable, they're not going to be quite linear. They'll still have a little bit of curvature, but they'll be close. Or if you had 3 cans of Pepsi and no Coke, or 3 cans of Coke, no Pepsi, or 2 and 1, or 1 1/2 and 1 1/2. So you're going to get indifference curves that are linear in the case of perfect substitutes. In the case of perfect complements, let's think about, say, left shoes and right shoes. Those are examples of perfect complements. Left shoes and right shoes. And let's again number it. Let's just say 1, 2, 3, 1, 2, 3. Let's consider a pair of shoes. 1 left shoe, 1 right shoe. 1 pair of shoes is right there. Now, let's suppose you've got 1 right shoe and 1 left shoe, and then all of a sudden you get another left shoe. That would be this point right here. You've got 1 right shoe and 2 left shoes. Does that extra left shoe get you anything? Of course not. You've still only got 1 pair of shoes. So you would be indifferent between this point and that point. Or, let's suppose you have 1 left shoe and 2 right shoes. That's right up there. Well, you're still indifferent between that point and this point. In other words, what we see is that your indifference curves, in the case of perfect complements, would look like L's. If you've only got 1 left shoe, it doesn't matter how many right shoes you've got, because you need 2 of them to make a pair. Now we could think about having 2 left shoes and 2 right shoes. That's a point right up here. Say right there. Now you've got 2 pairs of shoes, but having a 3rd right shoe, that doesn't make you any better off. Or having a 3rd left shoe, that doesn't make you any better off if you've still only got 2 right shoes. So this would be a higher indifference curve, but it's still going to be L-shaped. So you can see that with perfect substitutes, the indifference curves will be linear. With perfect complements, the indifference curves will have L shapes. Now we're typically not going to be thinking about perfect complements or perfect substitutes, so ours are not going to be linear or L-shaped typically. They'll have some curvature, but this curvature, the amount of it, tells us something about the substitutability or the complementarity of the 2 goods. In our next chapter, or excuse me, our next video, what we're going to do is we're going to pair this up with the budget constraint. And that will allow us to figure out the optimal bundle that this consumer is going to choose. So I'll see you in that video.